Okay, so we're going to start looking at some other types of reactions, and one we're going to study in pretty good detail here are oxidation reduction reactions. So, yeah, there's some other types, acid bases, we've done a little bit of those. Precipitate reactions, we've done some of those. Now, oxidation reduction involves oxidation and it involves reduction. We'll have to figure out what those two vocabulary terms mean, but they're going to both involve transfer of electrons. Electrons are going to be lost and electrons are going to be gained. And to know how to determine the number of electrons, which item loses, which one gains electrons, we're going to have to assign oxidation numbers to each particular atom that's in the chemical reaction. So, vocabulary, what are oxidation and reduction? Well, we're going to get a little more detail, but this will get us started at least. Oxidation involves losing electrons. Reduction involves gaining electrons. So if you were going to show that in a chemical formula, if you have electrons on the right-hand side as a product, yeah, we can, with other reactions, we can kind of think as producing, but in this context, we're going to think about products as they're going out, they're being released. And so these 4 electrons are being released in this chemical, this half reaction. Why is it a half reaction? Because it is only half of the entire reaction. In oxidation reduction reactions, something is going to lose electrons, in this case 4 electrons, and then something will have to gain electrons, in this case 4 electrons. So when we combine those two reactions, we add up all the reactants and place them on one side of the equation. I know that the overall reaction doesn't mention those 4 electrons. I'll put those in right now, and you'll see why they weren't in there initially. And then you add up all the products, and you put them all on the other side. And I know that these two don't look like this. This is really Mg with a +2 and O with a -2, and yes, you had 2 of these, so they just combined to make, so that's why you see it as MgO right there. So let me erase that, but then let me add these electrons. So a net ionic, or in this case just a net reaction, is if you see something that's exactly the same on both sides of the, I know it's not a equals here, but think about this in mathematical terms, an equals, but for us an arrow, they can cancel. If there'd be anything else that we would see that are on both sides of that arrow, we could also cancel those. And that doesn't mean they're not important. That just means that they're not being gained or lost. That means something is losing and something is gaining, but overall they're just being transferred. Like we could think about money. Someone would take $5 out of their wallet and they would lose $5 if they give it to somebody else. That other person gained $5. So there was a transfer of $5 in this, not a chemical reaction, but in that process. So if you didn't quite get all that, no big deal, because we're going to definitely revisit this multiple times before we think we have it mastered here. You can always call it oxidation reduction reaction. Some people shorten it and just call it a redox. So if you're not really good at memorizing, you could use one of these little ideas. Oil rig. Oxidation involves loss, and rig part would be reduction involves gain. I'm not really too partial to the Leo says Gur, but that's another option for you. So we're going to definitely study something called oxidation numbers, and that's going to help us define what's being oxidized and what's being reduced in the chemical reaction. So what are oxidation numbers? The number of charges the atom would have in the molecule or compound if electrons were transferred completely. And we'll figure out how to do that in a second here. Used to identify which elements are oxidized or reduced. And I already mentioned that that is why we're going to think oxidation numbers are useful. Oops. Okay, now you must follow these rules in sequence, not out of sequence, in sequence. So if there is a elemental in the chemical reaction, we're going to assign it an oxidation state of 0. What are elementals? They could be a actual metal. They could be we're going to see these too often, but they could be a noble gas, or they could be a diatomic. Those would be, I think, your 3 most common elementals. Okay, let me erase that. What's a monatomic ion? There's a monatomic ion. So that has a +2 charge. It has a +2 oxidation state. Alkali metals, if they're in some kind of compound like that, that means that it has a +1. If it's an alkali earth metal like that, calcium is a +2. So that's how you're going to go and navigate rule number 3. Oops. If there's oxygen in the compound, it is almost always going to have a -2. And I said you got to follow these in sequence, because if the oxygen was in there as a elemental, well, now it has a 0. So you have to hit these in sequence. There is an exception to this -2 idea, and that's peroxide. Peroxide is a polyatomic ion. It doesn't look so polyatomic, but it is. There's 2 oxygens in that compound. The most typical peroxide would be hydrogen peroxide. I think about the only other one you might see would be sodium peroxide. Okay, but for the most part, you're going to have oxygen in a -2 state, unless it's elemental from rule number 1. Hydrogen, almost always a +1. Unless it's in the back here, it's the anion of an ionic compound. That's not going to happen too often, but if it does, it's a -1. Rule number 6, fluorine is always a -1. The other halogens in that same column are going to have some different possibilities. And the rules 1 through 5 are going to help us determine what that will be. And we'll practice a few of these, and you'll kind of see how that's going to work. Number 7, if you know all these rules number 1 through 5 or 1 through 6, you add those things up and it has to equal 0 for the compound, or if it's a polyatomic ion, like if it was phosphate, when you find the oxidation state for phosphorus, and for each of the 4 oxygens, when you add all those oxidation states up, it better equal -3. If it was sodium sulfate, when you add up the 2 sodium oxidation states, the sulfur, and the 4 oxygen oxidation states, that better equal 0, because that's a neutral substance. These rules will are probably not going to be very significant to you until we start using them. So I think we're almost ready to start using them. We have a couple Not going to come up too often for you guys, but organics are a little tricky. Why are organics a little tricky? Well, first of all, they have hydrogen in it, most of them. And hydrogen is kind of in column 1, but it's kind of in column 7. So that kind of makes it interesting. And then carbon is in the 4th column of the periodic table. And if you remember, it ends in S2P2. So it could add 4 more electrons to get a full octet. It could also lose 4 electrons to get to the previous full octet. So that also makes it interesting. So assign oxidation numbers to all the atoms except carbon using the previous rules. Basically, I just threw in these two because those are the two most common you're going to see in organics. And then once you have that done, then and only then did you go over to carbon and see what's going on with carbon. So let me give you an example of that. Actually, 2 examples of that. Let's do maybe the easier one first. So oxygen has a -2 oxidation state, but there are 2 of them. So total on, like if I kind of like divide this up, it has a -4. So because this has it's a neutral compound, that means that carbon in this case must be a +4. So what we would say is that carbon has a +4 oxidation state, and oxygen has a -2 oxidation state. Okay? Each oxygen. You don't look at collectively all the oxygens, you look at each one individually. So it said hydrogen was generally going to be a +1. And if we look back, number 5 rule was for hydrogen. Now we didn't get a chance to use rule number 1, 2, 3, or 4 for that compound. So a lot of times you're going to skip some of these rules. So hydrogen has a +1, and typically, by the way, people don't even say oxidation state; they just say +1. Okay, and then since each hydrogen has a +1 and there are 4 of them, collectively this whole side is a +4. So the carbon would have to be, in this case, a -4. So just because carbon's a -4 here doesn't mean it's going to be a -4 the next time. Okay, so let's give some of these a shot here. So you're going to go through your rules, 1, 2, 3, 4, 5, 6, 7, whatever, and see what applies. I'm going to go back and forth. I'll do one of these completely for you in terms of going through all the rules. So rule number 1, all substances in elemental form. Do we have any elementals? No. And by the way, I'm doing the first one here, lithium hydroxide. There's no elementals. So the next rule, monatomic ions. We don't really have any monatomic ions there. That would be like if it was just lithium plus or whatever. So nothing yet. Rule number 3, alkali metals have a +1. Okay. Now we're talking. So lithium has a +1 oxidation state. There are 2 lithiums, so +1 times 2 is a +2. So the oxygen, without even looking at any rules, has to be -2. But we also have a rule that says oxygen is typically going to be -2. So we had 2 ways to approach that one. Okay, so the potassium in KClO4 is the first thing we get to because it's an alkali metal. The next rule we're going to get to for if we run through all those is oxygen being a -2. And then we don't have a rule for chlorine. We have to figure out what chlorine is. So we have a +1 for the potassium. We have a -2 for oxygen times 4 of those -2s. So this is all a -8. Collectively, this all has to equal 0. So what number could we put here to add to +1 and -8 to get a 0? I think the only thing we could have put in there was a +7. A +1 and a +7 and a -8 equals 0. So in this case, the chlorine has a +7. Now it looks like I'm making these as charges, and that is my fault. I should really go like, this is a -2, this is a +7 oxidation state. The oxygen is a -2 oxidation state. Okay. Calcium hydride. Calcium has a +2. And the hydride, each hydride has a -1. Okay, so now we have polyatomic ions. Well, we don't have a rule for chromium. Nowhere, no how do we have a rule for chromium. But if you go series down, we get to a rule for oxygen. Oxygen is almost always a -2. So what is chromium in this case? So a -2 for oxygen times 7 equals -14. This time it has to be -2 when we're all said and done. So what could we put here so that would equal that? I think if we do a +12, that would work. But how many chromiums do we have? We have 2. So each chromium would have to be a +6. Sodium is an alkali metal, so that's a +1. And then oxygen's always a -2. Whoops, not always -2. And peroxide, it's a -1. And how do I know that? I could do it a couple different ways. A +1 times 2 is a +2. What number, if I put a -1 times, there's 2 oxygens, that would give you -2. And again, this is not a polyatomic ion, but a substance that's neutral, so it should be equal 0. Next one, phosphate. Oxygen's almost always a -2. -2 times 4 is a -8. So if we did a +5 here, that would give you an answer of -3. So phosphorus is a +5. Here are a bunch of typical reactions that involve oxidation reduction. I'm going to do a couple of these for you here to kind of prove that these are oxidation reduction. And very likely you're going to have to do this on the test in some kind of chemical reaction. I'm not going to do all these, but I'll do a couple here. So aluminum is an elemental. Bromine is an elemental. So those both have zeros. I would always start elementals because that's rule number 1. Bromine is a -1 and aluminum is a +3. So let me just actually break this down for you here. Aluminum into half reactions goes to aluminum +3. That doesn't look like it balances, does it? I have one aluminum on the left, one aluminum on the right. In that respect, it balances, but the charges don't balance. And if you remember correctly, I claimed that this was an oxidation reduction reaction. So it's either going to have to lose or gain electrons. If I have it lose 3 electrons, on the left side, I have a total charge of 0. On the right side, I now have a total charge of 0. So that is a half reaction, and so this is actually the oxidation half reaction. And then the other one would be bromine, the elemental, going to, and we'll balance this later here, goes to Br minus. I'm just looking at each individual. So we definitely need 2 bromines. I know that that doesn't look like it looks like 2 bromines there, and we'll get there. We'll figure out how I got to the 3 there. And then we're going to have 2 electrons transferred in this reaction, gained in this case. So this is the reduction half reaction. So I said when you get to a overall reaction, you can't have any electrons. Something has to gain the electrons, something has to lose the electrons. Well, it turns out if we would multiply this entire reaction times 2 and multiply this one by 3, I think we might be able to see how this works here. I'm going to rewrite this now with the times 2 or the times 3. And the second one we have, whoops. We have that. And then does anything cancel before we add them all together? Yes. And that's always going to happen. So here is a reactant. Oh, it's the same reactant we have there. Here is another reactant. Oh, it's the same reactant we have here. And then if we take this and combine them together, we would actually get 2 aluminums like we have, and 2 times 3, 6 bromines. So there is our other material. Okay, let's erase that there. So all I really wanted to do in this part, we'll get to more practice of that later, but all I really wanted to do with that part is to just show you the oxidation states. So let's do another one here. Elemental. It's not very good. 0. +1, -1, +2, and each of those is a -1. So zinc goes from 0 to +2. That's one of our half reactions. And it looks like hydrogen goes from a +1 to 0. That's our other half reaction. So the zinc is being oxidized, it's losing electrons, and the hydrogen is gaining electrons. A couple other one of these. We won't get into the biological reactions. You can visit those if you take some organic at Pine Richland, or if you take organic or biochemistry or some biology courses in college. So what would a typical question look like? Well, I've kind of went over one of these already, but let's give these a shot. Right, the oxidation half reaction and the reduction half reaction. So to be able to do that, we have to have a good idea of the oxidation states. By the way, do you see that there's a sulfate here and there's a sulfate there? Because the polyatomic ion doesn't change from left side to the right side, I know that the oxidation states are also not going to change with sulfur and oxygen that are in SO4. So I could go and visit what those would be, the oxidation states, but I think we can leave those out, and you can see that other items are going to be part of oxidation reduction. The copper over here is elemental, and the copper over here is a +2. So if I wanted to pluck these out, I could go zinc going to zinc +2, and then to get this to balance, I need electrons, and you can put the oxidation or reduction wherever you want. I'll put it above the arrow here. And then the other chemical is copper +2 going to going to copper metal. And in this case, I'll have to put the 2 electrons over here. And again, if the electrons are on the left side, it's reduction. If the electrons are on the right side, it's oxidation. Sodium bromide plus chlorine gas, elementals. By the way, if you can identify elementals in the chemical reaction, those are always, not sometimes, always the things that are going through oxidation reduction. So chlorine on the left side is a 0, on the right side is a -1. Bromine Br2 on the right side is a 0, on the left side is a -1. So there are our items. So bromine -1 going to Br2, we'll have to go and do that. Electrons on the right side, so that's oxidation. And then chlorine gas going to chloride ions. We'll put the 2 electrons over here, so that is reduction. Okay, this one looks like it's a lot more intimidating here. So I said if you have any elementals, they're going to be part of the oxidation reduction. Well, there's no elementals in here, so that's off. But we do have a monatomic ion of a +2 going to a +3. So a +2 to a +3, let's write that out. Don't worry about the coefficients right now. So where would I have to put electrons so that this balances, so that it's the same charge on both sides? If I put 1 electron right here. Electrons on the right side make this oxidation. So you haven't seen any of these before. I've seen a lot more than you have here for oxidation reduction. I will give you another clue. Again, if you had elementals, they're always going to be part of this oxidation reduction. The other item that's typically going to be part of oxidation reduction is transition metals. And it turns out the Mn that's in these 2 compounds, I think is going to change oxidation states. So let's erase that. So oxygen is always a -2, almost always. There are 4 of those, so that's a -8. The whole thing has to come out to be a -1. So in this case, manganese would have to be a +7. So I'm just going to put a +7 here. And then on the other side, same exact idea. Oxygens are -2. There's 2 oxygens. That's going to give you a -4. This is a neutral molecule, a neutral substance, so manganese would be +4. So +7 and +4, they're not the same oxidation states, so therefore it changes oxidation state. Okay, we don't know how to balance this yet, so we're going to lay off on balancing this, but we do know there's going to be a transfer of electrons here for sure. It looks like every manganese changes from a +7 to a +4. But let's lay off trying to balance that. We're going to learn how to balance that on another lesson. Okay, and then the last one, this is an interesting one down here. Why is this interesting? Because we only have 1 product. So somehow it must be involved with both oxidation and reduction. And that's not going to happen that often, but it does happen. So, elementals, 0. This one over here, this iron is going to be a +3, and this iron here, whoops, not a +3. I don't know why I did that. +2. And this iron over here is a +3. So iron +3 to iron +2, whoops. and then iron 0 to iron +2. So it doesn't really matter which one we write first. To balance that, let's put an electron there. So that's reduction. And then the other one is iron 0 going to iron +2. And I think we're going to need 2 electrons there. Okay. So other than this one right here, we haven't let any of these go except for that one about where these electrons are. But since we had electrons already on the right side for this one, oxidation, we know that the electrons, we don't know how many, we'll leave that as a question mark, but they're going to have to go on this left side here. Okay. And that will get you guys started, and we're definitely going into a lot more detail on that, but I think at this point you should be able to tell me what is being oxidized, what's being reduced, and tell me the oxidation numbers of the different items in the compound.